So let's talk about some general properties of graphs. These are going to be things that we are interested in for pretty much any function that we talk about. What can we say about pretty much any function whatsoever, just generally speaking. And then eventually, for the specific functions that we're interested in, are there certain specific features and characteristics that only those might have? So this is more the general sort of thing. Broadly speaking, what kind of big things are we looking for no matter what kind of graph, no matter what kind of function we might have? So ZERO is one of those things, and that is any number that makes our function into a zero, into the number 0. So any x value that we can plug into our function and then calculate, it spits out a 0. Usually I spell this out, ZERO, just to make sure that people know what I'm talking about. Now, that splits things up into where the function's positive, where the function's negative. That might not be nearly as interesting as what the function is actually doing. Is the function going up, increasing, as we move from left to right? So we're taking the same sort of convention as we do with reading words, with reading graphs. We're going to go from left to right. Is the function going up? Decreasing, is the function going down? Constant, it's staying level. One of the things about reporting this behavior is we're again talking about x values, so from this x value to this other x value, and we keep those to be open intervals. So parentheses only. We're not using any brackets when it comes to reporting this kind of behavior, only open intervals. So from this x value to this other x value, only using parentheses. Then, when things change from increasing to decreasing, when things change from decreasing to increasing, then we're talking about other stuff that we're interested in. A maximum, so going up and then tipping over and coming back down. We've got a maximum happening versus a minimum, so a dip, a valley. And we say relative in these two definitions because we're referring to what is around that spot. Technically speaking, we could have something that's really funky, like we're looking at stuff and we go, hey, it looks like, we just kind of, bleep, top out. But maybe there's something really funky that when we zoom in on that, and we realize it's actually not just tipping over, maybe it's wobbling as it's still growing. And we didn't get that sense. You kind of think of like a map with the coastline. You get the general sense of what that coastline looks like from this big old map, like zoomed out, Earth size. But then when you shrink down and say, okay, well, what if I'm just looking at the coastline for one specific country? Well, now I've got a lot more detail going on. I got a lot more of what's happening with the changes to that coastline. And then if we zoom in even further, what about the coastline right here along Jacksonville? We're going to get even greater detail. So we've got to keep in mind those sorts of weird things that can happen. And we're talking about just what's nearby, relative. Now, once we've got a list of all of these relative maxima and relative minima, we could try to say something, if possible, about an absolute maximum, which would be capital T, the highest y value, period. Or capital T, the lowest y value, period. Nothing is higher than that absolute maximum. Nothing is lower than that absolute minimum. But we've got to start with the relative stuff. So let's take a look at an example here where we can start putting stuff into some context from right to left, or from left to right. Whoops. From left to right. From left to right. So we've got an arrowhead going on here. That arrowhead pointing downward, pointing to the left. Not by much, but it is pointing to the left. So this graph would continue in this fashion. If we had a bigger sized grid, we would see more and more of that. So if we just start here with this arrowhead, we know that that's going to keep going down, but we want to move to the right. So as we start moving to the right, we're tracing along this with our finger. What is our finger doing? Is it going up? Is it going down? Or is it staying level? Well, it's going up. Then we hit this spot right here where we move from going up to then going down. So right at that spot, we have what we were just mentioning, a maximum kind of idea. Relative to what's nearby, we've got a peak. But as we're tracing, our finger goes down, 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 and then bottoms out. We switch back over, we start increasing again. We peak out, and we start decreasing, and then we hit that arrow that says we're going to keep going down and to the right. So now we can talk about what's happening here with increasing, decreasing, constant, relative maximum, relative minimum sort of stuff. We've got that increasing business that we were tracing out that was going to be happening from the far left up to that first blue dot that we've got. So from the far left, that means x value, negative infinity. Not really an x value, just negative infinity is what we're saying, because we keep going forever to the left. That's going to be doing the increasing stuff. The farther I go, the farther out I start doing the increasing. How far can we go? We can go forever. So negative infinity. Coming over this way, coming over this way with the x values, -3, -2. Open intervals, so I don't get to include this. There's something special going on where that blue dot is. So when we talk about increasing, this first chunk of graph that we hit before this blue dot, that's increasing. We're going to represent that with the interval negative infinity, comma, -2, parentheses on both of those. Parentheses on the negative infinity part because that's just part of our rule for the interval notation. Parentheses for that -2 because we said these are all going to be open intervals. We're not going to be having any of those brackets showing up with our increasing business, with our decreasing business. We go all the way up to, but we don't get to land on that x equals -2. All the way up to, but we don't get to land on it because there's something very special happening at that x value. Speaking of, at that x value of -2, we would have a relative maximum. So we can go ahead and switch on over and say at x equals -2, we have that maximum. But that's just where it's at as far as the idea of paying attention to x values. What is the maximum value that we actually land on? That's going to be a y value. So y value of 1, y value of 2. at x equals -2, our y value is +2, our y value is a relative maximum. One of the things that we might want to pay attention to is how things are phrased. And a lot of times you will find this sort of question phrased in two different parts. Where is the maximum? It's at x equals -2. What is the maximum? Y equals 2. So the where is based on those x values, because that's largely what we're paying attention to. But what is the maximum value of our function? Now, function values are y values. We've got to report a y value for the what is the maximum. What is the maximum? What is the minimum? Those are going to be y values. So we want to make sure that we're paying attention to what it is we're being asked to report. We don't want to give an x value if they're expecting a y value. We don't want to give a y value if they're expecting an x value. So we're going to pay attention to that sort of thing. As soon as we pass that tipping point, we start to decrease. So when we go to our description for decreasing, that would begin just on the right side of the -2. That would go up to x equals 0, not x equals 0, go just up to the x value of 0. We're going to stop right before that because of that whole open interval business. We hit that purple dot that's there where we bottom out, minimum. At x equals 0. And if we look at our grid markings, what is the minimum? The minimum is y equals -2. Again, assuming the most basic markings on our grid are going by ones. X equals 1, x equals 2, y equals -1, y equals -2. So that's our relative minimum. It's at, where is it at? At x equals 0. What is it? It's y equals -2. As soon as we pass that bottom out, that trough, that valley, we start increasing again. So more increasing stuff. So that's going to mean we add an and. That's going to start parentheses 0, comma, all the way up to that next blue dot. That next blue dot happens where x is equal to 3, so that's where that interval is going to end. X equals 3 is where that interval is going to end, and putting in the parentheses for that open interval. Hitting that next blue dot, that's another relative maximum. Again, relative to what's nearby. This one's way far away in the grand scheme of things. This one's way far away. This, just relative to what's nearby, if we just kind of zoomed in on that, that's a maximum. At x equals +3. What is that maximum? Well, 1, 2, 3. That maximum is y equals 4. So we would want to write that in there. And once we pass that, after that second blue dot that we see here, everything else is decreasing. That's what that arrow is suggesting there. That arrow is suggesting that we do not get any other changes in the direction of things. This isn't going to somehow bottom back out and shoot back up again. Nope. We would have had to make sure that that's represented before we put an arrowhead in there. That arrowhead is telling us that's going to continue to the right and downward. So everything else past this is going to also be decreasing. So we're going to have to write that in as another chunk of decreasing behavior. So that is the parentheses 3, comma, infinity for that. Now, the next stuff is not necessarily as interesting to us to talk about, but it can be helpful. So we do sometimes want to investigate whether there's anything special about how a function appears, behaves, and that's regarding the idea of symmetry. Now, symmetric about the y-axis, so that's like a mirror image, right? Bloop, bloop. Symmetric about the origin, that's a little bit more unusual because that's not necessarily thinking of something that is like a mirror. The origin is a point. How on earth do we have a mirror that's just at that single point? That's kind of on the weird side. What's happening here when we talk about that symmetric about the origin business is that something in the upper right would have to actually spin around and down to the lower left if instead we were talking about something that was in the lower left to begin with. It's going to spin around and up to that upper right. So there's that kind of reflecting business that's happens kind of like a double reflection. If we reflect and reflect, woo, there we go. And if we reflect and reflect, yep, there we go. So you could say that this symmetric about the origin is like this double reflection. Take that reflection left to right, take that reflection top and bottom. And so if we do that, there we go. If instead we're starting down here, we do a reflection, doesn't matter which one we do first, but we get that right kind of orientation happening. The functions themselves we call even or odd. So what's happening then is that we can test out a graph if we've got a graph. We can test out a function if we've got the actual equation for the function. F of x equals x squared plus 5. If we want to test this even versus odd, the other option would be neither. Even versus odd, or neither. We're going to plug in the negative x, and we're going to see what's going to happen there with that. This is like saying, if we pick something that is on the left side of our graph, will it be a mirror image of what's on the right side? So we take our function that says x squared plus 5. Instead of the x, we're putting in the negative x. Well, if we square a negative, we get a positive. The plus 5 isn't changing anything. So the expression that we get is exactly the same, x squared plus 5. It's exactly the same as that original function. If that's the exact same as our original function, then this says no matter how far you might travel to the left, you're going to get exactly the same thing as you would if you travel that far to the right. So if we talk about, I'm going to pick something off to the left like a negative 5, I'm going to plug that into my function, I'm going to get some sort of y value coming out of that. I'm going to get the same y value as if I plugged in a positive 5. Negative 10 versus positive 10, same y values are going to be spit out of my function. So that means same y values, stand where the light can hit me, right? Same y values on the left and right. That's symmetric about the y-axis. That function is even. So, jot that down. Now let's say we take a look at a different function. Fifth root of x Again, we want to look at what happens when we go off to the left. So negative x is going to get plugged into that function. Instead of the x being underneath of that root, or underneath that radical, depending on if you prefer radical. So depending, you put in, instead of the x, a negative x in there. Now we want to be able to compare this with our original function, so we've got to remember a little something about odd roots. What number raised to the 5th power would give me a negative? Well, that would be a negative number. So we're actually allowed to take the negative that's inside of an odd root and plop it outside instead. Which means that if that negative is sitting out in front, it's no longer inside of that root anymore. What is inside that root instead is only the x. Well, 5th root of x, 5th root of x. This version of what we're seeing here has a negative, but then the other part is exactly that original function. So negative version of our original function, negative f of x. So we went off to the left and we said, what's going to be happening over here to the left? Well, we got some sort of y value, but the way that that y value turns out is it got flipped over to the right, but then it got changed to the opposite. So if it was up here to the right, it got flipped down. So was over here, now it's over here. That's that flip, that mirror image. Well, hey, what if it was down here instead? What if I went off to the left and I had a y value that was down here instead? Then if the negative is out in front, that changes it back up again, but the original y value would have been off to the right. Oh, hey. So that's down here, comes to up here. That's that symmetric about the origin business. That's that function is odd business going on. And so, just to make sure, in case it's not obvious, if we try to take our function and plug in the negative x, and what happens is not getting the original function, not getting the original function that now has a negative out in front of it. If it's anything else other than those two outcomes, then we would say the function is neither even nor odd. We would say that the symmetry is neither about the y-axis or about the origin. We can't necessarily say anything about any kind of symmetry that there might be. There might be symmetry. We just can't figure it out from that limited information that we've gotten by trying to take our function and plug in a negative x. So this is not necessarily quite as useful to us as being able to talk about the increasing, decreasing, constant behavior, as being able to identify relative max, relative min. But we might be interested in doing that sort of test, finding out about that graph, finding out about that function, even versus odd, symmetric about the y-axis versus symmetric about the origin. If we do know those things, that's helpful. If we don't know those things, then, well, we didn't really lose out. So again, these are nice things that we can talk about. over and above what we've already mentioned as far as the basic ideas of domain, range, x-intercepts, y-intercepts. So increasing, decreasing versus constant behavior, relative maximum versus relative minimum, even versus odd, symmetric about the y-axis versus symmetric about the origin, or neither even nor odd, neither symmetric about the y-axis nor symmetric about the origin. It's a handy sort of collection of things to know about. And then we'll want to start investigating more. We'll leave that for the next video.